So yes, good afternoon and welcome again. This is the Communication and Signal Processing Seminar. We are halfway through the semester. So I'm delighted to welcome Ramtin Pedarsani from the EC department at the University of California, Santa Barbara, who is our speaker today. I would like to welcome him in person. Of course, he may not like the weather here today. It's starting to get colder, so maybe a virtual seminar is better. Anyway, he's an assistant professor in the EC department at UCSB. He obtained his PhD in electrical engineering and computer sciences from UC Berkeley in 2015. He received his MSc degree at EPFL in 2011 and his BSc degree at the University of Tehran in 2009. His research interests are quite broad. He's been going to talk about machine learning related problems, but he's also interested in optimization, information and coding theory, as well as stochastic networks. In fact, a lot of his thesis work was with Jean Morin, where he did a lot of things with stochastic networks, including cloud computing related topics there. So he's a recipient of the Communication Society and Information Theory Society Joint Paper Award in 2020, the Best Paper Award in the IEEE International Conference on Communications, ICC, in 2014, and the NSF CRI Award in 2017. Before I cede the floor to him, I just wanted to acknowledge a few people. Shelley Pearlkamp has been the organizer, and she's done a yeoman's job behind the scenes, as well as I wanted to acknowledge the supporters of this seminar series, which is KLA, and the two research groups, which is NCIS and Signal Processing, Machine Learning, and Image Processing. Anyway, so Ramtin, the floor is all yours.
Thank you. Thanks for the nice introduction, and thanks for inviting me. So today I'm going to talk about federated learning, which is a kind of hot topic these days in distributed machine learning, and it has many applications in healthcare, in semantic learning, in autonomous systems, and so on. And as I will explain, still it faces a lot of challenges. And today I'm going to focus on these challenges and try to design algorithms that make federated learning faster, more communication efficient, and more robust. So to give you some motivation, these days we have a shift of paradigm in machine learning, or we expect to see a shift in paradigm, in the sense that we move from centralized machine learning, or even machine learning that is done in cloud, towards machine learning done at the edge of the network. And the reason for that, at least partly, is that we have data being gathered a lot at edge nodes of the network, and a lot of this data is private. For example, our text messages, our images in our cell phones, healthcare-related data, and so on. So such data has to remain local for privacy purposes, but we still want to learn a machine learning model on this data. And the other reason that is exciting to do machine learning at the edge is that we don't want continuous transfer of this data to the cloud or to a central node. That will incur a very large communication cost given the amount of data that we are collecting. So it would be much better to actually learn common machine learning models using this data, which remains local at the edge node. So in terms of computing, this paradigm shift is basically from central computing to cloud computing, and now to edge computing. And with this motivation, I'm gonna specifically show you the differences between centralized machine learning and federated learning, and what we really mean when we talk about federated learning, because this term is quite broadly used these days. So in central machine learning, the idea is, if we want to do central machine learning with our data of cell phones, let's say, so these clients' devices will gather data, for example, images, and their goal is to learn a shared model. And then this data should be transmitted to a central node or to the cloud. And then we can do some SGD algorithm or whatever to learn a machine learning model. The issue is, well, the privacy is not preserved anymore. It has very high communication requirement bandwidth, and the training would be slow because we are not using this computational power that we have across all these edge nodes. So in federated learning, what we want to do is still this data is gathered at the edge nodes. However, it will remain local. So how we can train, still our goal is to train a learning model, let's say theta. So what we can do is we can use the computational power of each device in order to run the training algorithm distributedly and then aggregate at this parameter server or central node. So the architecture would work like this. Let's say you are currently at some iteration. So these machine learning algorithms, they are typically based on some iterative gradient-based algorithm. So let's say at iteration t, you have theta t for your model. This will be broadcasted to these devices, or it will be downloaded by the devices. And then at that point, there will be some steps of stochastic gradient descent based on their own local data. So you are going to get, if you have like m devices, you are going to get m new models. And then these will be sent back to this aggregator or parameter server, and then there will be some aggregation, typically just averaging and projection, and you get the new model, and this will continue. Okay, so there are pros and cons for federated learning. You can have lower latency. So the reason for this is, again, we are using this computational power of many devices potentially, and the communication load is smaller. It is clearly more privacy preserving compared to central machine learning. So we don't need to do actually data deployment. And we use less power compared to cloud computing. We are essentially using the computation power of these edge devices like our mobile phones. And finally, since we can scale this, we can use many data points of many clients, we can learn smarter models. But still there are many challenges. So some of these challenges are kind of both challenge and benefit. It is true that communication is better than sending all the data to the cloud. However, still these vectors, these learning models, let's say they're edges of a neural network, they can be huge vectors that have to be transmitted to this parameter server at every round of this iterative algorithm, which can be very expensive. We may still have some privacy leakage. It is not completely privacy preserving. It's of course much better than sending our data to the cloud. The reason is that even if we do one or some steps of gradient descent, given the knowledge of the previous model and the new model, something can be inferred from your data points. So if the parameter server wants to learn something from your actual data points, information may be leaked based on the update that you sent. And the other challenge in federated learning is that since we want to scale the system, include many clients and devices, in general, this data may not be IID across devices. So still the goal is to learn a common model. So this data, for example, all of them are images or text messages. But each device has some preference, some bias. For example, in text messaging, you may use some words more often, or your images may have particular brightness background, which makes the data points non-IID. And then simply solving the expected risk minimization may not be efficient for heterogeneous data. The other challenge when we scale the system, this is for any
So
distributed.
Ramtin, a quick question. So when you say
Yes.
non-IID, is it at one device, or you're saying that it's possible that the same data has been
Yes.
used
So
by multiple devices because you're getting different views of the same data?
yeah.
Which sense of non-IID is it?
So here what I mean is non-IID across devices. So per device, we assume, so you may also say this is not a good approximation, but this is kind of the case in any machine learning model that per device, we assume the data points are IID. However, across devices, they may not be. Okay, so by non-IID, I mean the data points of device 1 is coming from distribution P1, device 2 is coming from distribution P2. Still, they're independent in our assumption, but they are not necessarily identically distributed. But also we assume that the distributions are related. They are not like completely off. I don't want to learn some machine learning model from your text messages and my images. I mean, that's meaningless. Both of them are text messages. However, there's a difference in distribution.
Well, I mean, I could be looking at the same image, right? So in that sense, so I was just curious about the independent nature across devices.
Yes, so across devices, the assumption is that basically this is maybe not 100% true, but if I'm taking image 1, 2, 3, whatever, these images are independent from the images that you are taking. But you are right, maybe there is an event which is very popular and we all go there and take similar images. So there is an approximation, but it is kind of common. This is in any machine learning algorithm that you assume you have some distribution and data points are coming from that distribution independently. Now, if you have multiple distributions, they still come from that distribution independently. In the assumption is this, but there may be a difference in the distributions. And the reason for this, in the end, it won't matter for our results if our objective is only to minimize empirical risk. But since we want to connect empirical risk to expected risk, we need some independent assumption like this.
Thank you.
Thank you. Okay. So device heterogeneity is another challenge. So basically, in any distributed computing system, when you scale it up, you are going to have some nodes, some machines that are faster in computation, and some who are slower, and we call them stragglers. And this is more drastic in federated learning because it depends really, for example, on the battery percentage of your device, on how new your, let's say, iPhone or smartphone is the new iPhone 12 or iPhone 3, or hopefully not iPhone 3. So this can have very wide range of computation capability. And this, as I will explain, is a synchronous algorithm in general. So waiting for the slowest node can slow down the training a lot. And finally, there is robustness issues against particularly adversarial attacks, like adversarial examples perturbing the data points, or even some nodes may be malicious and they send results to the parameter server that are adversarially designed so that the algorithm is screwed. So these are basically the challenges that we need to resolve, and I'm going to focus on some of them in this talk. In terms of application, so federated learning was first proposed by Google as an architecture of learning, and it has been applied to applications such as Google Keyboard and other applications. So I'm sure this, when you send your emails, you have seen this feature that the next word is suggested and so on. Now Facebook is doing it, and so it has a lot of applications, and we expect to see more applications, in particular in the automotive systems and in healthcare, where we want to really have a privacy sensitive learning algorithm, which also uses the data of a lot of patients or healthcare data of a lot of people. Just a quick summary of some related works. So the first paper by Kairos et al. That I have in this list is a survey paper. I just checked today, and it has more than 200 citations. This 2019 paper, it's a nice survey paper. So clearly my list cannot be extensive. This is a very hot topic with many people working on different aspects of federated learning. And these aspects, as I said, include non-IID data, the issue with local updates, as we will kind of discuss here, privacy, compression methods, and so on for communication. If you're interested in federated learning, I encourage you to read the survey paper. FedAverage is like the first paper by Google, and some of the recent works that have addressed some of these challenges. So in this talk, what I'm going to focus on is the first part about communication efficient federated learning and kind of simple method to handle stragglers. But the main focus is on communication, and in particular, what we can say about the optimization problem and statistical guarantees when we add quantization noise to the vectors, if we want to actually reduce the communication load by quantizing the vectors. And this is a joint work with my student Amir Hossein Reisizadeh and my colleagues Aryan Mokhtari at UT Austin, Hamed Hassani at UPenn, and Ali Jadbabai at MIT. So this is one paper that I will quickly go over. And the second part of the talk, I'm going to focus on robust federated learning as a method to address data heterogeneity and essentially the theory of minimax optimization in a federated setting. And this is a joint work again with my student Amir Hossein, Farzan Farnia, who is a postdoc at MIT, and Ali, my colleague at MIT. So these are the two papers that I will have an overview of them. So as I explained, in the first work, we look at two of these challenges that are system challenges in federated learning. So in particular, communication load, because we have to repeatedly send these updated models that are very large vectors to the parameter server, we want to reduce communication load. So to do this, there are two simple ideas that we do. One is we communicate less frequently. Two is that we send quantized vectors, so we compress these vectors and send fewer bits. The issue with that, so this will kind of solve the scalability issue partly, but the issue with that is, well, we may, if we don't do this carefully, we may pay in terms of optimization guarantees and statistical guarantees. And also we may have stragglers, so we want to understand if we can have a deadline-based algorithm. So we will see a simple thing that we can do to handle stragglers. Just a quick note that I want to make here is these two challenges, actually I've been working on kind of a related topic, and I know some people in Michigan are interested in this topic as well, which is called coded computing, and how we can use coding and introduce coding in our algorithm, coding theoretic ideas, so that we tackle these challenges of straggler and communication. And I worked a lot in that area. And it is kind of particularly not suitable for federated learning, which I'm going to explain as a side parenthesis. The reason is that in coded computing, what we do is we have this data that we encode in cloud. We have access to all the data, so we can encode part of the data and use that as a redundancy in order to remove stragglers, reduce communication. And so we are in control of the data, and then we can use it in many algorithms, in many iterations of an algorithm. However, the whole point of federated learning is that data has to remain local, so I cannot see the data of any device. And they shouldn't actually share information, share data. So in federated learning, we kind of require simpler ideas to handle this communication straggler issues. The challenge would then go on the optimization side, that if we use these simple ideas, do we lose anything in terms of optimization guarantees or no? Okay, so with this focus on system challenges, I'm gonna go to explain essentially two benchmarks in distributed stochastic gradient descent and Fed average, the benchmark proposed by Google, and see how we can modify them and get a communication efficient algorithm. So distributed SGD, if I want to explain, so my optimization variable is xk at iteration. The idea is that this will be shared with the nodes, and then there will be one step of SGD taken on this. So this one step is important. And we get new updates, xk1 up to xkn, and then this will be sent back to the master node, to the parameter server, and average. So this algorithm is very easy to analyze. It works out nicely. The reason is that our update is indeed an unbiased estimate of the gradient, right? So we just take one step of SGD, we take the average at the master. So we indeed have an unbiased estimate of the gradient in our final update. This is not good for federated learning. The reason is that we have to communicate at every round. So what Google proposed in Fed average algorithm was, okay, let's do multiple updates per device. So we have xk, we are gonna have tall rounds of SGD, so per device. So they kind of continue learning on their own and infrequently communicate and take the average at the parameter set. So the issue here is that, well, clearly this update is not anymore an unbiased estimate of the gradient. And the analysis of this is challenging. So what we propose in our paper, the algorithm is called FedPAQ, is that still we have this architecture. So we are gonna have two modules basically here. We are gonna have these multiple local updates. This time, instead of sending the actual difference of the vectors, we are gonna send the quantized version of that. Moreover, we are gonna set a deadline such that the stragglers are ignored essentially. So we are gonna have a subset of devices that are active. And this will further actually help us in terms of communication. And by the way, these local updates and this quantizer will also add privacy to our algorithm. The reason is that once you have multiple local updates and then you add the quantization noise to it, it's harder to infer something from xki minus xk, infer something from this, something from your data point. To summarize, our algorithm, FedPAQ, is an iterative algorithm that has these modules. So it has periodic averaging, infrequent communication. which has the advantage of less privacy leakage, fewer communication rounds. It has model quantization, which I will go over what we need for this quantizer function, and we will see an example of it. So we reduce the number of bits that we send, and finally we have partial device participation, which enables us to handle the stragglers and make it more scalable. And by the way, in this first work, we are assuming IID data for our theoretical results. So this is an overview of the algorithm. As I said, the main challenge is, can we prove that this algorithm converges? How fast? What are the trade-offs? And so on. Any questions about the architecture of the algorithm, the modules? It's very simple, actually. Just periodic averaging, quantization, and partial device participation. Okay, so now let's take a look at the quantizer that we use. So what we need theoretically is basically this unbiased property. Expected value of the quantized version of x should be equal to x, and the variance should grow in a bounded way with norm of the vector. So expected value of q of x minus x squared should be smaller than q norm of x. So we need these two properties. Now we can use any quantizer that has these two properties for our theoretical analysis. One particular case is the low precision quantizer proposed in this paper. And the idea there is quite simple. Basically, you send the norm of the vector, and then you preserve the sign at each entry, and you have multiple levels of quantizer. So you randomly quantize a number to an upper level or to a lower level, such that it remains unbiased. So I won't go to the details, but for example, if you have essentially s equals 1 means you have 3 levels that you send either plus 0 or minus together with the norm of the vector. What you do is, if you have you send the norm, if you have positive entry, you either send 0 or 1 with some probability so that it remains unbiased, and if you have negative, you either send 0 or minus 1 again to make it unbiased. And you may ask, okay, a real number, what does it really mean in terms of number of bits? So what we assume is a real number takes 64 bits to be sent, but there is indeed some quantization happening there too. But we don't consider that in our, let's say, bias calculation, so it's unbiased. Okay, so with this, let's see our theoretical guarantees. The main problem, so here is where the IID data comes. The main problem is expected risk minimization, but we always solve empirical risk minimization in machine learning. So n devices, m samples per device. And the assumptions that we have are quite standard here. IID data, smooth loss function, or Lipschitz gradients, what we know about the quantizer that I mentioned, unbiased and bias bounded stochastic gradients when we do local updates. And we don't have the assumption. So this is actually a key point compared to prior work, is that we don't need any assumption on the actual gradient being bounded. And that assumption is actually not a good assumption to have, because if the optimization is not, if the domain is not constrained, having a bound on the gradient is not really meaningful. If you have function x squared on R, the gradient is not bounded. So we remove this assumption, and that's a kind of key technical contribution of the proof together with the quantizer. And our results, we have two results. One for the strongly convex case, where we have tau number of local updates per round and k number of communication rounds. So k times tau is essentially capital T, like the number of iterations, right? Because there are tau updates per round and k communication rounds. So if we pick the right step size, we can indeed show convergence to the optimal point, and the rate would be like tau squared divided by capital T or k tau. And this is indeed order optimal for such problem, distributed SGD type of problem, despite having the local updates and the quantization nodes.
So, Ramtin, just in that,
Yes.
where does the quantization come in? I mean, it seems like that's
Yes, so they are kind
constant,
of
but
hidden in
maybe,
these
I mean,
constants. Yes, so this is a good question. So the quantization, uh, the variance of quantizer is kind of captured with this small q, right? So those are hidden in the constants here, but we assume it's order 1. Okay.
okay, so I'm just saying, does it come as q squared or q cubed or an exponential q? I mean, what, in some sense, how does that play a role? Would you be able to shed some light on that?
Yeah, so I don't exactly remember, but I can double check the paper and get back to you offline. But my guess is that it will actually show up linearly, because these variance terms in general, when we do, this is the variance term, right? So when we do this optimization analysis, in general, these variance terms show up actually linearly in our upper bound. So my guess is it actually appears linearly in the constant.
Okay.
Okay.
Well, thank you.
You're welcome. So for the non-convex case, where we cannot show convergence to the optimal point, of course, what we can show is that essentially converges to a stationary point, or on average, the magnitude of the gradient becomes small. And this happens with rate 1 over root t plus tau over t. So basically, this is the upper bound that we can establish. And the key challenge in the proof, as I explained before, is this fact that we don't have unbiased, and because tau is not equal to 1, we don't have unbiased estimator of the gradient. And due to this, we indeed need to, and moreover, we don't have the assumption that gradients are bounded, so we don't have a uniform bound on this bias. So we need to do extra work essentially for this analysis. But I don't want to go to too many details.
So just a quick further question on this. In this case, are you basically you assign it to all the devices and they compute? It's not, you're not giving to a partial subset in some way.
It does, actually, it does. But
so there must be some sense in how many you send it to that matters as well. What is the, I mean, what is the guideline do you need? There are
so
n, do you?
Yes.
Do you give order n, or do you need to do order square root n, or what does it, I mean, there are n devices in some sense.
Yes, so in the analysis, basically what we assume is that there will be all of them active at each time. And since the data is IID, it really doesn't show up anymore in terms of like which one was the straggler, or which one were participating, which one was not participating. If the data was not IID, then it would be important actually. So this is actually a good motivation for the second part of the talk, that if you just don't use the data of a particular device and the data is not identically distributed, then it will be problematic, because you cannot anymore converge to the optimal solution, or even in the non-convex case, converge to a stationary point.
But somehow that thing should come in the trade-off, right? I mean, instead of your time to, I mean, it's almost like you have, suppose
So
there are n
the
devices. Let's say,
analysis is not in terms of wall clock time. The analysis is in terms of number of iterations, right? So if I
okay,
have
so number of iterations, then that makes sense. Okay, that accounts for it. Basically, it was, yeah. Okay, that makes sense.
exactly, yeah. But this is a very good point that you are raising, that you, in the end, you care about the wall clock runtime. So it is important to, if you want to, for example, set up a deadline, depending on the distribution of the computation time, you want to know how many devices, when should I set my deadline, so that there is this trade-off between like how many of them participate versus how many of them, versus how long I wait in each round to proceed. So this, as I said, this is not capturing. This analysis is based on just the optimization number of iterations, and we assume there are these many active devices in each round. Okay. So let me just show you a couple of plots quickly before I'm a bit behind time. But so one thing to practically observe is that this parameter tau, number of local updates, if you increase it, it means more local updates per round, which means less frequent communication. So clearly, and this is also clear from our bounds, with smaller tau, you have better accuracy in terms of your convergence rate, but you have fewer communication rounds. So this is the trade-off that you're also kind of mentioning, that is showing not for stragglers, also for communication issue. So how often should I communicate? Should I sacrifice a lot for about the accuracy and then communicate less frequently, or what? So this is something that if we have a model, we can analyze, but we have also done numerical study on the neural network, and it's 50 nodes and so on for CFAR10 data set. And we observed that comparing to two benchmarks, Fed average, which doesn't have quantizer, and QSGD, which has tau equals 1. So quantized, but only one round of local update per node. Our algorithm performs better, and indeed there is a sweet spot for this tau, even in our numerical results. So if tau is too small, it means too many communication rounds. If tau is too large, it hurts us in terms of accuracy. So there is indeed a sweet spot. That was for the non-convex case, neural network. For strongly convex case, we see similar behavior. So we did logistic regression on MNIST here. Yeah, so maybe if there is a question on the first part, this is a good time before I kind of shift gear and talk about robust federated learning and data heterogeneity. Okay, so first part of the talk, we handled or tried to handle the system challenges, communication, straggler. But we assume data is IID, but this is what we know, that data distributions vary across the nodes. And indeed, there are results that show Fed average fails drastically with heterogeneous data, even if the amount of heterogeneity is not large. And the observation is that this heterogeneity is really device dependent. As an example, for images, samples on one device can undergo same distortions or same features like brightness, intensity, contrast, so on. So based on this, the model that we consider and try to adapt to federated setting is the following. So there is a model distribution, PXY, X is the feature data point, Y is the label, where is generating basically these samples, but a transformation of them will appear in each device. Okay, so samples are drawn, and this transformation here is linear. So sample is drawn from this model distribution and then goes through an affine transformation and becomes sample of device. Okay, and in particular, this affine transformation has two parameters, the matrix lambda I, which both should be, these you can think of them as perturbations. So lambda I minus identity matrix have bounded norm, and delta I is the perturbation to the data point is also bounded in L2 norm. Okay, and this actually matches, but it's another motivation, but it does match the problem of adversarial machine learning or universal adversarial perturbation per device. So another way to look at our model is that, let's say they all have data points coming from the same distribution. However, an adversary is perturbing the data point of the device I according to this universal perturbation lambda I x plus delta. And still we want to learn a common machine learning model on this. So we introduced the problem of distributionally robust federated learning. Basically, this is a min-max formulation of the empirical risk minimization. So still we have average loss that we want to minimize. W is the optimization parameter, the edges of the neural network if you want. I changed the notation, so sorry for this. X is now, since I want X to be my data point, Y to be my label, W is the optimization parameter. But then we have this perturbation or transportation variables, delta and lambda. And we introduce this min-max formulation of the problem. So we want to minimize the empirical risk subject to worst case transported data under these constraints, that there should be a bound on the perturbations. Okay. And the important thing is that we still need to solve this in a federated setting. We want to solve this problem with low computation and communication costs. And the way we do this, so we basically use Lagrange multiplier lambda to bring in the constraints. So, and we have a local penalized loss for each device. And then we have a global loss, which is just sum of these local losses. And we want to minimize this function f over w and maximize it over psi, which is the collection of lambdas and deltas. And we want to solve it in a federated setting, so low computation, low communication. But this is the framework that we introduced to address the heterogeneity issue. And the algorithm that we propose is that, again, it's an iterative, low communication, low computation algorithm in the following sense. So in each round, what happens, think of the previous algorithm, Fed average. We don't have quantization here, just a simple case Fed average. We still have multiple local updates for parameter W. However, we also, this is the gradient descent. We also have a gradient ascent because we want to maximize over lambda and delta. We also have gradient ascent locally done by each device on its lambda and delta, but only once per round. Okay, so tau updates for W per round, one update for lambda and delta per round. So, and indeed, the update on lambda and delta is based on gradient ascent, and on W is based on gradient descent. So essentially we are introducing this concept of federated gradient descent ascent algorithm, and we wish to analyze it. And the advantage is, again, it's computationally easy to solve because per device we are just computing gradients and we are communicating not frequently. Okay, so let me show quickly the convergence results that we can show for Fed Robust. So we have non-IID data, but there is a bound on the degree of this non-IID-ness. And the way we characterize this, and this is typical in the literature. So without those perturbations, so for psi equals delta equals 0, lambda equals identity, we have a bound on the variance of local gradients with respect to the global gradient. So this essentially puts a measure on the degree of non-IID-ness. And then we have a regular assumption for stochastic gradients, unbiased, variance bounded. We have loss functions are smooth or Lipschitz gradients. And then for the, so this problem is minimization, maximization, right? So it may be non-convex, non-concave, or it may be convex, non-concave. You see, so we have to consider different scenarios. And actually, because of the regularization that it was introduced, this problem is indeed concave in lambda, and specifically it has the PL condition, which is kind of a weaker version of strong concavity. So it is strongly, you can think of it like strongly concave over psi, and either strongly convex over W or non-convex over W. So similar to before, we have two cases of convex or non-convex for W, but over psi, we assume it is strongly concave. But it, indeed, in the paper, it's PL condition, which is weaker than strongly concave. So with this, the way we can actually analyze this is based on a potential or Lyapunov function that measures the optimality gap. So the first part of this function essentially measures the gap of W with at iteration t with W star. The second part that measures the gap of psi with psi star. But anyway, I don't want to go to too many details. What we can show is that we can analyze this, and we can indeed show that this achieves with right choices of step sizes eta 1 and eta 2, it achieves near optimal performance of log t over t. Optimal is 1 over t. For the convex concave case, and in particular, as special cases, it recovers prior works in the literature. Two special cases. If we have tau equals 1, so simply non-federated minimax optimization, it recovers prior work in the literature. And epsilon 1, epsilon 2, 0, which means non-robust federated learning, it recovers the prior work in the literature. And we also have similar result in terms of reaching stationary points for the case that we have non-convex concave. And again, this recovers the two special cases that I mentioned in the prior work. And let me quickly talk about the numerical setup. So we tried this over TensorFlow, different neural network architectures with 10 nodes, each 5,000 samples. And during training, what we did was we perturbed with random Gaussian vectors, but during test, we actually perturbed these data points adversarially to capture the min-max effect, the worst case effect. And we did this in two ways, both with adversarial perturbations by state-of-the-art PGD algorithm, projected gradient descent, and also with this affine distribution model. So as I said, this is closely related to the adversarial learning setup of Madri et al. And so on. That's why we compared with them as a benchmark. And overall, we observed a much better performance of our algorithm compared to Fed average, which is not robust, but also comparable or better performance with adversarial training. However, remember the advantage of our algorithm is that it is much faster than adversarial training. It's just gradient descent ascent in a federated setting. Adversarial training can be very costly computationally. And actually in our simulations, even it's 4 times faster than adversarial training. With this, I'm gonna wrap up the talk. So I think I can skip this slide and talk about some future directions that I'm working on. So in this talk, I talked about FedPAQ and Fed Robust, 2 algorithms that we have recently proposed for fast and robust federated learning. There are interesting future directions. So one is this issue of device heterogeneity and statistical accuracy. And going back to the question that Vijay asked and our conversation with Lynn this morning. So basically, if we just simply, in a non-IID setting, if we just simply ignore the straggler so that we gain in terms of speed, what we have observed and systems people also tell us is that the stragglers are persistent stragglers. They are not random stragglers. So they indeed remain to be the same devices that are slow during this training time. So we are not just using their data, which can be very bad. We have these fairness issues in machine learning and statistical accuracy will be low. So we have to somehow find a fundamental trade-off between device heterogeneity and statistical accuracy. And our idea is that essentially we start the algorithm by participating the fast nodes so that we get to a good solution, reasonable solution. And then we bring in gradually the slower nodes as we proceed. So we improve the statistical accuracy. And in this way, we don't kind of get stuck by stragglers throughout the algorithm, but also eventually we use their data points. And then we are working on privacy preserving federated learning as well. And there are multiple interesting directions that other groups are also working on, like malicious nodes. What if instead of affine distribution shift, we have general distribution shift? So it's not linear, it's coming maybe from a neural network. And then there is this problem of multitask learning that can we actually learn or one machine learning model per device? Instead of learning one model for everybody, can we learn one per device and later adapt it for new devices and so on, which is called multitask learning. And with this, I will conclude my talk. I again want to thank my collaborators and thanks for your attention and coming to the talk.
So, Ramtin, I had a quick question before we sort of switch to the discussants.
Sure.
So if in some sense you're saying that I'm going to run so many updates for every device, but won't you sort of change the number of updates based on your capabilities? If you're a straggler, you run fewer updates.
Yes, so this is a very good point. So what you are suggesting is that if a node is a straggler, maybe it runs 2 updates, but if a node is fast, it runs 10 updates, and then they aggregate the results together at the master node. So we actually, this is a good point, and it works well in practice. We try to prove that we can indeed have convergence to the optimal point. And it actually doesn't work easily, especially for the non-convex case. And I would say that the reason for this is, so if you kind of have in the non-ID case, right? So what can happen with this issue of like having fast nodes participate more than slower nodes is that the solution of the slow nodes may actually go to another sort of local optima compared to the local optima of the global function. Because of their fewer participation rounds, and the fast nodes will actually get to another local optima. So it's a bit hard to explain, but in the non-convex case, since we have these multiple local optima, we may not get to the consensus if they don't participate equally.
Yeah, I can see the challenge there. No, thank you.
Yes.
So let's go over the discussions next. I think, if I remember correctly, I think Sue was going to take care of the first part of your talk. So I think I'll let him go first. And then Sheru was going to do the robustness part, so she can go next. So Sue, if you want to present your slide, you should have co-host status already. So.
Okay, so I stop sharing.
Yeah, thank you.
Interesting. Well, you see my slide?
Yeah.
Okay. Yeah, so basically I'm looking at the Federated PAQ from a distributed optimization perspective. So just let me give a real quick overview of this paper. So the main challenges of this paper I want to solve for usual basic federated learning is two challenges. One is communication bottleneck, which we actually want to send the updates in a compressed manner and more infrequently. And second is the scalability issue. Those devices might not be always active all the time. So FedPAQ used three techniques to encounter these challenges. One is periodic averaging, which means that the process only takes the average once every tau local descent. And second is to use partial node participation. So each time only R nodes participate in the local descent, and R could be less than N, which is the number of agents in the system. And third is message quantization. So a little bit, so I just have some observations. The first one is, so there are two very common distributed optimization schemes. One is the so-called master-slave, and one is the full distributed. So in master-slave, there's a master, which is the information aggregator, and this master is linked to all the nodes, and it will maintain an authoritative copy of the decision variable. And basically, this paper falls into this category. Whereas the other scheme is there's some underlying communication graph, and there's no master to coordinate the whole learning process. So the agents can communicate with its neighbor, and they need to coordinate the learning themselves. So for centralized optimization, the convergence rate is basically 1/t for strongly convex function, and 1/square root t for general function. And you can see that this paper is actually achieved this. So this is this part. The second observation is for the periodic averaging. So for at least the distributed optimization scheme I usually see, there's two processes. One is the consensus process, and another is the main convergence process. And usually the consensus process will be the fast process, while the central path convergence will be the slow process. So what do I mean by that? Let's see a graph. So here I have two nodes, and this is their objective. And this is the sum of their objective. So you can see that they started from A, and then the first node will do one local descent to B. Second node will take a local descent to C. Then they will take a very average from B and C, which leads them to D, and then they will take the local descent again. So the distributed optimization scheme is basically I want to start it from A, and then I want to converge to this optimal point. So there's the two parts of the convergence. The first part is basically they iterate from different nodes want to converge to a consensus. And so this is what I call the consensus convergence part. And then I want this consensus to converge to the actual optimal, which is what I mean by the central path convergence. So usually in distributed optimization scheme, they will use the 2-time scale process where the consensus convergence is the fast process and the central path convergence is the slow process. But I think one of the main contributions of this paper is to they sort of use a different scheme. So they have a frequency for how often we want to take this consensus step. So this frequency sort of represents a trade-off between the amount of communication required and the convergence speed. And one more thing is it could actually not converge if you doesn't do the consensus step frequently enough. So why is that? Let's see. Oh, yeah. So this is what in the algorithm. So this part is doing local descent, and this part is doing consensus. And this is they are not following the usual 2-time scale process, because you can see every tau iterates, they will do once consensus, and basically because they are the master slave scheme. So basically the consensus convergence is just one shot. I take one average, and then it will converge to the consensus, the right consensus. But I only do this once every tau steps, and this tau becomes a tunable parameter. So this graph is showing that I take 3 local descent, and then I take average. So you can see I take 3 local descent, and then I take average. So you can imagine if you take the average not frequently enough, you will stuck at some point where in local descent step, they will descend to their own local optimal. And then after taking average, it will go back. It will never be able to reach this global optimal if you don't take the consensus step frequently enough. So one contribution of this paper is to characterize, okay, so this tau shouldn't be more than square root of t. Yeah, another thing is the partial node participation. So it's quite like the asynchronous schemes in the distributed optimization literature. So I give a reference to one of Professor Mermin Wei's paper. So you can view this as in the fully distributed optimization setting, the consensus step is basically multiplying the decision tuple with a doubly stochastic matrix. And for partial node observation, you will only see the many zeros in it, but the bottom line is as long as the product of them multiplies to the O1 vector, then it will still converge. For the quantization part, it's basically introducing noise, and the thing we want to ensure is to ensure those noise are wiped out by the decreasing learning rate. And I give a reference to one of Professor Nidish's paper. That's all of my slides. Thank you.
Thank you for the nice summary and other references.
So Sheru, do you want to just quickly summarize, take your discussion, present your viewpoint on the second paper?
Oh, yes.
So, Sue, you'll have to stop sharing. Yeah.
I think I already stopped.
No, but your thing is still coming up. So yeah.
Is it good now?
Yes. Let me. Okay. Yeah, can you see my slide? Yeah, actually, my discussion is mainly focused on the federated learning part for both works, actually. So for the robust federated learning part, I didn't write down the summary, but I just have a couple of questions for the speaker. And as mentioned in your talk, you also compared it with the adversarial training, and there is a connection between the framework you presented and the adversarial training. But in the paper, it seems that the adversarial training is only you are only considering this additive perturbation. But actually, there is a type of attacks which is the spatial attacks, and which somehow is like a affine transformation. So in this case, I was wondering, is this framework becomes the same as this robust adversarial training, and this work proposes the algorithms in this distributed version? And
yeah, good question. Thank you. So in terms of yes, if you have basically an affine transformation like this, the model covers it. So it's for any affine transformation. However, the bound is on basically this matrix that you have cosine minus I. So that minus identity should be smaller than epsilon. So for us, the bound is actually the difference in Frobenius norm of identity matrix and lambda. But here, to me, it seems that this matrix is more general, because I don't necessarily see that there is such bound here. For delta is clear, so delta should be bounded. So maybe there is a difference here. The other point is that when we say adversarial training is a little bit different from adversarial examples. So the point is this: we are assuming that actually the data points can be adversarially perturbed with this matrix like lambda and perturbation depth. However, what we are saying, so our message is that we can indeed defend against such attacks with a simple federated gradient descent ascent algorithm. Adversarial training, however, refers to producing such during training phase, producing such examples and then solving the optimization problem. So basically what we wanted to say is that adversarial training is very powerful, but it's very costly in terms of computation in a federated scenario. However, even a simple gradient descent ascent in a federated setting, which is federated friendly, is performing as well.
I see. Yeah, thank you for your explanation.
Thank you.
Yes, and actually, I have I prepared something for the first work, and it's not like the question, but maybe some potential directions for the extensions that I wanted to hear your thoughts. The first is the partial device participation that in the algorithm, and in your algorithms, R nodes are selected uniformly at random. I was wondering, is it possible to generalize it to the setting when the nodes are not uniformly selected? Because it is a really common scenario that some nodes are updated more often than the others. And in this case, if different devices, the data on the different devices are not IID distributed. So in this case, maybe the global model at the beginning, they will more skewed toward the local models of those nodes that at first, and will gradually correct it with until the busiest node is updated. So in this case, maybe many communications are not necessary. So maybe the best thing for us to do is to update all the nodes at the pace that according to the busiest node. Yeah.
Yes, very good question. So just one clarification that I need to do here is what I presented today is kind of a modified version of the published paper. So in the published paper, we actually have this uniformly at random, but later we observed that, okay, if we have stragglers and we set a deadline and they all have the same distribution, it will be exactly selecting them uniformly at random. But you're mentioning an important point, which is what if there's heterogeneity? And the heterogeneity is actually twofold. You're saying maybe some of them are stragglers, and if we set a deadline, the same one will be against straggler, because that's the slow node. The distributions are not the same. So for example, let's say one of them is exponential 1, which is, let's say, slow. The other one has computation time exponential 100, which is very fast. So then that's very good point, that if we just set a deadline, then we do not actually get to see the data of that slow node. Now, the second point that you're saying is that, if I understand correctly, is that why don't we just proceed with the fast nodes, and then it's not necessary to have the updates from the slow nodes, and we can later add them to gain the statistical benefit. And this is exactly what we are working on actually right now. So we are using your suggestion that what if we start with the fast nodes and later we bring in the slower nodes, so that we have first less communication, second faster computation time. So did I answer your question kind of correctly, or?
Oh, yes, actually, I was thinking we should start with the slowest node. I mean, we should pause all the updates. It's like for those fast nodes, because if we update based on those nodes, then the global model will be more secured towards those local nodes, but may not necessarily be the...
That is correct, but it is more important in the end of the algorithm, actually. So in the beginning, so your intuition is correct. However, in the beginning, our initial W is just completely off. So if we just progress fast to something reasonable, it doesn't have to be optimal. You know, in the beginning, we just want to get to something better as an initialization, so that later we bring in the slower nodes. Okay, so it is in the end that actually it's important to bring the slow nodes, because that is where we want to converge to the optimal solution.
Yeah.
But this is a good point. Yeah, very good observation.
Yes. Yeah. Yes, thank you. And indeed, I have another questions. So also in the algorithm, it's the fixed fraction of devices are updated in each iteration. So So suppose that we have this communication limit, so that we only a fixed number of devices can get updated during the entire iterative process. So I was wondering, is it important or is it possible to find the best way to distribute the number of updated nodes across the entire iterative process?
Yeah.
Because yeah.
Go ahead. Sorry. Go ahead.
Yeah, because the step size decreases over time. So I was thinking maybe for the nodes that are updated in the initial stage, they are more important. So maybe we should try to distribute more nodes in the beginning to save this communication.
Yes. So one clarification, actually the step size is 1 over, if I remember correctly, capital T. So if you want to run this algorithm for 1000 iterations, you then fix the step size based on that. You can also making it time varying, but because of this reason, actually, we have a step size which is a function of the capital T, the number of iterations that we want to run it. If I remember correctly, maybe it's in the second paper, but definitely in the second paper, the step size is fixed. But even if it is decaying, what you are mentioning is correct in the sense that why do we want to have a fixed fraction of devices? It's kind of related to the previous question that yes, indeed it's better to make it adaptive. Indeed, it is better to make it adaptive. The reason we have fixed or we set a deadline and we pick the fastest, which end up being a fixed fraction of devices in expectation. The reason is, well, our primary purpose here was just the analysis of the optimization to be complete for the first time. Now you can even go beyond that. You can say that if I have a fast device, this is exactly Vijay's question. If I have a fast device, I have a slow device, and I know which one is fast, slow. Maybe I should have more local updates at the fast device, fewer at the slower device, and then somehow aggregate them smartly. These are all very interesting directions that should be actually followed, but still we don't have a kind of complete characterization of this trade-off between stragglers, computation time, and the statistical accuracy and optimization guarantees.
Oh, yes, sure, yeah. And so the last one is about this quantized message passing. And I was thinking that this, although adding this quantizer actually helps to improve the privacy because it's more difficult to infer the true data. And I was thinking that maybe it can be used directly for preserving the differential privacy, which just add a noise to this vector. And for this mapping, it is the unbiased and with the bounded fixed variance. But in your analysis, the assumptions on the quantizer also satisfy the two these two conditions. First is the unbiased, the second is this variance grows with the squared of the L2 norm. So I was thinking that maybe is it doable to somehow relax this assumption?
So the issue is once you add the noise, remember in the end you want to send fewer bits, right? So you want to, for example, send only plus or minus or 0. If you add noise to X, then you have to even quantize that again, right? So just X plus noise is still a real vector. It is true what you are saying about the condition, but it is not saving me in terms of number of bits. But what you are saying is interesting in this sense. So what if I first add the noise due to differential privacy that I want, and then I quantize the whole thing? Yes, so that actually probably will cost us, in general, you know, in all these differential privacy preserving works in federated learning, there is a cost that we pay to have differential privacy in terms of convergence. So there is a cost that we pay. Even in numerical results, we see that we don't get to the optimal solution. So we do pay a price, but there's of course a balance between these two.
Okay. Yeah. Yes. Thank you.
You're
yes,
welcome.
that's it. Yes, answers my question. Thank you. I think that's all my
Ramtin, there was one more question in the audience. So Ranjan, I think you can go ahead and please ask your question.
Can you hear me?
Yes.
Yeah, so I had a question like from the very beginning. So you were talking of centralized learning, and then you went to federated learning, and you said that one of the disadvantages of centralized learning is that it is slow. Am I correct?
If it is done in one machine, yes.
So my question is, what I couldn't understand here is that if you're doing centralized learning, then you're just doing it once on the server, whereas on the federated side, you're iterating time and again. We don't know how many iterations it will take. So how can you say that, like the centralized case is like slow training? I mean, it could well be the case that the federated is slower, right?
So in terms of, it's just parallel computing, basically. If you think that that machine has the same computational power of these nodes, they are, just think of it as when you parallelize the computation to n nodes, they are making progress simultaneously towards the solution. Okay, so actually the speed of computation, the wall clock time to reach the optimal solution becomes n times faster if we ignore the overhead and communication. If you do it in one machine, you are doing it sequentially. Okay.
Right, but if you're doing it on the cloud, so they have much more power than your individual devices. So how does
So
you're not
cloud
you're
is
not
a different story. Cloud is still distributed computing. However, most of the time for that will be taken by actually transmitting this huge amount of data to the cloud, which is kind of, anyway, for federated learning, it's not feasible, because the primary goal is that the data should remain local because of privacy. But
right.
you are right in the following sense: if we just completely don't care about the privacy.
But even in federated learning, you're sending, right? Even in federated, you're sending not the data, but the model on the latency channel, which is the communication channel. So that's the same thing, right?
So that we have to send anyway. Even in the cloud, that communication should happen.
Exactly. Right, but that there in the cloud, you're sending it once. Here, you're sending it time and again. So basically, like
even in the cloud, you have to do it multiple times. I
Okay.
mean, still you have to do the iterations, right?
Okay. Okay, thank you.
Yeah.
All right, so Ramtin, thanks again for an excellent talk. Yeah, and I think you're meeting with a few people tomorrow as well.
Yes, yes.
So let me just give you a clap from our side. It's not the easiest way to do this, but thanks again for this. Thank you for both the discussions as well.
Yes, I again thank you for the invitation and the discussion and the good questions. So I look forward to the meetings tomorrow. Have a good day.
Can I ask a quick question?
Oh, sure.
So with
actually, can you take this offline? I think it's going on too long. Sorry. Yeah, I just wanted to. I mean, it's gone much longer than I wanted it to.
So you can send me an email, also.
Okay. Thanks.
Yeah. Thanks.
Okay. Bye-bye.